You guys have any questions while I'm going through them? Just ask away. You might have to at me though, so I can. Or actually, you might have to speak up. But maybe I should turn on streamer mode. How do I turn that back on? Um, Recording. Okay. So, mm, okay. So for the first problem set, you have a code says register 2 is initialized to 2, and then you have list the sequence of instructions that we execute on pipeline during the first 2 iterations of the loop. Okay, so basically, code will run line by line. So definitely 1, 2, and 3, because those are just load and R types. Yeah, so load, R type. This is a branch. There's a R type and also an R type. So the first 4 instructions will run. We didn't mention anything about branch prediction. So you'll just fetch the next instructions, the next 2 instructions. So that's how it always is. Um, but then we'll see what is the values. Let's see. R1 will have some value. And then R1 get that value. R2 is initialized to 2, so 2 minus 1 equals 0. Well, it doesn't matter for this question because he didn't mention it, but like let's say like there was like a branch predictor taken, then you wouldn't fetch 5 and 6, you would fetch 1 and 2 after line 4, right? Yeah, so these 2 lines are gonna get flushed, right? Because branch are not equal. So yeah, 2 is not equal to 0, so it will go to the thing. So like these lines 5 and 6 that it will fetch, it'll have to get flushed. So after those get flushed, it actually goes to the loop. So bring 1, 2, and again 3, 4, and then this time, oh, I just said 2 minus 1 is equal to 0. Sorry, whoops. And then this time it'll be 1 minus 1, which is equal to 0. So then this time, um, it'll still also get 5 and 6, but this time it'll be correct. Um, yes, you still have to show the flush because um, they're still getting executed. Like you're still fetching and decoding for the instruction 5, and you're fetching for instruction 6. So like technically they are executed. You're just like flushing them after. Yeah, it's not really asking like which one's like finish. It's like which one's like run. So so for data dependencies, part B, um, you just look at where the links are. So what I do is in the source of like the previous instruction, the register, and then like the destination line, I guess. So for this one, it's line 1 on register R1. Um, and then this is on line 2. So uh, yeah, so 2 has a dependency on 1. Maybe I should put it the other way around, but yeah. I'll just leave it like this. Fine. Is R0 used anywhere else? No. R2 is used for the branch. So the source is line 3, register 3, destination is line 4. V0 is not used anywhere. And then R1 is going to be used when you loop back up to here. So um, line 6, register 1 on instruction number 1 on second loop. Is there anything else? I think those are the only 3, right? So one here, one here, one. Oh no, is that this one? Yeah, the destination. Oh no, it's not. Oh, it's here, this one. Okay. Uh, so it's not instruction 1, it's instruction 2. It's sorry, it's line 2 is I think, right? Actually, no. Is that right? The source for this is here, but also over here. R1 plus 8. The loop would occur from line 4, wouldn't it? Uh, uh, let me think. Oh yeah, because these 2 lines only run. You're saying 1, 2, 3, 4, and then we loop back here. Maybe that's not right then. I feel like there's definitely like another one when I did this problem set, but I'm not remembering. Was there one? Does this matter? 6 on 1, even though it happens way later. No, doesn't, right? Like the the destination is like the source for this. So um yeah, that's why I think I had yeah. So I think this is not from the like the loop, but like even though it happens way later, there's still technically like a dependency you would have to write, even though like yeah, like the dependency won't matter. I think that's what like Vivek was saying in class. Um, but I feel like there is there anything else from the loop, or that's what I'm confused about. 1, 2, 3. Go. Oh yeah, this one on this one, I think, right? Because if you wrote it out, it'd be like R1, R0, R0, R1, R2, R2 minus 1, some branch. And then you have R1 again, R0, and then R0, R1. So this one right here is over there. That's what I meant. Okay, yeah, so it's the source would be the source is line line 2, register R0. The destination is sorry, this is line 1, 2, 3, 4, 1, 2. Line 1 on second, and then also I think there's one over here, like I was saying. I think. I think the source is 1 again, and then this is R1, and then the destination is line 2 on second loop. Let's see if I did that right. So yeah, it's 1, 2, 3, 4, 5, 6. So part A is right. And then for this one, it says instruction 1 has a dependency on R0 from instruction 2 on the second loop. So this one is right, right? No, is it? Or, oh no, this one, right? No, did I mess up? R0 from instruction 2 has a data dependency on instruction 1. Okay, I should have wrote it the other way. Fuck. Alright, let me write it on the right. Instruction, register, dependency on um, so instruction 2 has on R1 dependency on line 1 for R3 1, 1. Is that right? Did I fuck up? Dude, I'm like confusing myself. Um, did I do this right? Line 6 has a dependency on R1 instruction 1. 5 doesn't have it, right? And then R2 on instruction 3. Yeah. Line 2, R1 from instruction 1. And then Yeah, one on the second loop has a dependency on R0 from instruction 2 on the second loop. Oh, there should be two from instruction 2. 2 on, maybe it should be on the second loop here, right? I'm not really sure. No, no, I don't think that's true actually. Mm. 2 or 1 from instruction 1. Yeah. So how many are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, sorry. That was more confusing than it needed to be. But basically, if you have a loop, I would write out the next couple of instructions like this as well, and then just look for anywhere where the destination register is the source for a subsequent line of code. So there's one here, um, one here, uh, one all the way here. This is on the second loop over here. So where else? This on here. So does that make sense? Okay, I'm just gonna move to the next one. Start the pipeline diagram. Okay, so it's gonna be 1, 2, 3, 4, 6, 1, 2, 3, 4, 5, 6, and then every instruction will always fetch the code. I should probably write down what each one is. So this is a load, R type, branch, and R. Branch, R, load, R type, branch, R. Can we go over C like you're teaching for the first time? I read it, but I don't. Okay, so if you saw part A, uh, do you understand this? Like the order that the code is running? Right. So you just trace the code, and since it's pipeline, like for the branch, there's no branch prediction, so you just bring the next two lines of code anyway. These will get flushed later because this branch in particular will actually end up taking the loop, and then that's why you have one like all these running again. So this 5 and 6, I just put in parentheses just because like Vivek did too, but it's like to symbolize that they're getting flushed, but they're still executed. So for this, since you have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, put those in the rows, and then for pipeline, you have load, which is still fetch, decode, exec, mem, write back. For S type, it's fetch, decode, exec, mem, and then no op. R type, fetch, decode, exec, no op, write back. Branch is fetch, decode, exec, no op, no op. And then jump is fetch, decode, no op, no op, no op. So there's always 5 stages for every instruction now in pipeline. The first instruction, there's no possible um, hazards and stuff. So write S for stall and X for no ops or flushes. So the first, since it's a load, that's just a normal thing. Fetch, decode, exec, mem, and write back. For the the next instruction, um, we always, sorry, this is like cycle one, cycle two, cycle three. I'm just gonna label them. Sorry. So just like before, when you would run line by line, we try to run them as close to parallel as possible. So instead of like waiting for this whole instruction to finish, like normally you would have like the fetch, decode, and all that shit like after. We're gonna put it as soon as possible. We can't put it on the same at the same cycle because there's only you can only do like one stage at a time per cycle. So the next best thing is to do it like this. So it's always staggered like this. Um, so for me, I always do fetch and decode because those never have conflicts with anything else, I think. And then now we just have to think about are there any dependencies? So um, so instruction two has a dependency on instruction one, and that's because let me just copy this code so we know what it is. Oh, yeah, it's gonna be like that. Um, so for this code, um, what happened to my thing? Sorry, crashed. Wait, there we go. Okay, so there's this dependency here, right? Um, so that means that fetch and decode always will be fine. Um, when we try to load the data, we have to like know what this value is in R1, but we can't know that until this instruction brings back the data onto this register. And when is that going to happen for a fetch? Um, oh, for the exam, I don't think we would have gotten 2 hours for the final anyway, but he might have extended it like last time. Who knows? But yeah, sorry. So, uh, to know this value, because there's a dependency, we have to wait for this to bring the data and then put it onto register one. And that will happen during the write back stage, but we can get the data right after the mem stage. That's like one of the data forwarding things that he mentioned. So we can't get it yet because it has to finish this mem stage first. So we have to stall here. But then later, the mem stage, it'll be able to, after this mem stage is done, we can get it directly um, instead of having to wait for the write back because it's already on the processor by then. We can do that since write back takes 1 to 2 nanoseconds. Is that what it is? Because I thought it was because like this exact also only take 1 to 2 nanoseconds. I'm pretty sure it's just that like it can write it to the write back stage and also give it to like a whatever register is requesting it for the exec. The point is though, like after mem stage, like you don't have to wait for the write back. You can get the data. Um, so that's fine. And then since it's another load, uh, mem, and then right back. So that's fine. That's instruction two done. Next one, you keep on staggering these. So fetch is fine. You when you ever have a stall, this whole column will have to stall now from below. So this has to be a stall, and then it can decode after that because unless there's like stalls like fetch and decode, there's never any conflict. So you can like blindly put those in, uh, you know, accounting for stalls. Um, After that, you have to see is there any data dependency. No, R2 is not used, so you can just go to the exec stage for that. Um, so that will be fine, and then there's going to be a no op, and then a write back. So now that's instruction three done. The next thing, do you want to put fetch here, right? But you can't, like I said, because you have to stall. You don't have to write the stall, but put the fetch here instead. I'll put the stall here if you want. And then decode, no problem. So this is the branch, and the branch has a dependency on this R2 right above. So when will this be done? This will be done at the end of the exec stage. So um, normally you would have to wait for write back, but because of data forwarding, you can forward this data, um, and you can do the exec stage for instruction four right away. So these are the two types of data forwarding. Basically, if there's like something in mem stage, you can forward it, or if there's something in exec stage for an R type instruction, you can forward it. Um, so fetch decode exec and then no op and then no op. For the next instruction, we're going to fetch here. We're going to decode here, and then after this is done, we're going to know that actually um, the branch that we took, we don't need lines five and six. So we'll flush right here, right after this is done. So it's flushing that. Um, at the same time, at cycle 7, it was going to fetch, right? Because we only know after this is done, which is will be cycle 8. So as you can see, you fetch this instruction and this instruction, but they'll get flushed right after this is calculated, and you find out that okay, we actually do have to take the loop. So those two lines are flushed. Um, and now instead we'll fetch instruction one because that's where the loop is. And then from here, this is the same. No conflicts here, I think. Instruction one on second loop has a dependency on instruction two, but instruction two is already long done, like over here. So we don't have to worry about that. I'm sorry, can you repeat the flushing? Okay, so basically, um, over here, we always try to stagger the fetches, right? There's no branch prediction here. So even though this is like a branch type instruction for line four, um, we don't know if we have to take the branch or not yet. So with no branch prediction, you just fetch the next line because if you remember, like PC equals um, PC plus four, right? So that's just the next line. Um, so we'll fetch here and we'll decode here, and we'll also fetch like because we're still staggering these. But after this branch is calculated, which is at the end of the exec stage for branches, we'll see that, oh, we actually don't need lines 5 and 6 because if you saw here, it's if R2 is not equal to 0. And over here, he said that default, the R2 started with initially with 2. He gave that in the problem. So 2 minus 1 is equal to 1, and then 1 is not equal to 0, so we do have to take the loop. So since we realize that we have to take the loop, that means that the next two instructions that we fetched, 5 and 6, we actually don't need those. So after the exec, like the next cycle, we'll flush those two instructions and then fetch the right instruction. Does that make sense? For branches, it's always either you fetch the right instructions or you uh, wrongly fetch two wrong instructions. And then once the branch is calculated, if it's the wrong instructions, you'll just flush those two instructions. And then, like I was saying, for line 1 on the second loop, there's a potential data has there's a data dependency, but that doesn't mean that there's a data hazard. Because if you look at 1 on the second loop, which is here, it's dependent on line 2, but line 2 was already done at cycle 7. So by the time like this is running, you don't have to worry about it. So this can do its thing, no problem. And then there's also this 2 on the second loop, R1, instruction 1, and that'll be the same case. Instruction 1 will be long done by the time the second loop runs. So just like make sure that if there's like some dependency on the second loop, just see like, oh, is there some data like that I need here? Oh, but it's already finished by then, so there's no, even though there's a data dependency, there's no data hazard. So anyway, line 1 will be fine. Okay, so line 2, stagger. This will be the same case as before, where, because it's the same instruction, right? So we have to stall again because um, it's uh, dependent on, yeah, on the second iteration. It's still like the second loop's line 2 is dependent on the second loop's line 1. So same thing. So fetch decode, we have to stall until we get the data back from the mem stage, and then we can do the rest. And then this will be, it's because it'll be forwarded there. Mem right back. And then we want to fetch here, but we can't because there's a stall. So stall here, fetch code. What's the spec? No op, right back, right? Did I mess up? I think I might have messed up, right? Yeah, I did. I didn't stagger the fetches right. The fetch should have been here. And then this is stalled, and then decode here. Um, this one has no data dependency, so that's fine. No up, right back, yeah, okay. And then this one is the one that's stalled. And fetch, decode, same thing here, data forwarded here, just like the previous loop. No up, fetch here, decode. This time, 5 and 6 will run. Is there any dependencies? No, A0 is like not in this code, so that R type will be fine. Fetch decode exec, and no op, right back, and then stagger this one. Is there any dependency? I think there was, but it was not. 6 is on line 1. Line 1 is long done by then, I think. Yeah, line 1 was here. That's long finished, so no problem. Fetch decode exec, no op, right back. So that should be the whole pipeline for the answer. Let's see. So, oh, he wanted us to write X's for the no ups. That's my fault. But I don't know if he would take off points for that. But he wrote X here, but just write N for no up. Um, style fetch equal flushed. Okay, looks right, I think. Yeah. Okay. Any questions? Yeah, it's not that bad, but basically you just try to run the lines, and you just have to be careful for a couple of things, which is like the data dependencies, and then for data dependencies, like there's like the data forwarding, which are like there's like two scenarios from R type instructions exec, and then if you have a load after the mem stage, you can get that data. Um, and then branches, there was no branch prediction in this question, but basically it's either the branch is correct or the branch is incorrect, and then you flush two lines. So yeah, he said that he was definitely gonna put a loop for something. There's like a more annoying question than this where you have to calculate like the CPI, and it's gonna be really annoying. So yeah, it'll literally be like some code lines of code, and then he'll be like, do this, and then there'll probably be a branch predictor, and then he'll also ask us to calculate the CPI. So yeah, I mean, once it's over. For this question, during the fifth clock cycle, there's full hoarding and hazard detection. So you just draw out the pipeline, I guess. So there's line 1, 2, 3, and 4. 1, 2, 3, and 4. I'm just gonna not draw the lines, but it's more messy, I feel like. Um, yeah, should. Oh, I don't know. So this one is a L type instruction, R type. This is a L type, and this is an R type. For the first stage, maybe I will just draw the grid. Should I? I don't freaking know. Um, hold on. I'm going to copy this. Let's see. Does this work? Perfect. Okay. Okay. So, um, 1, 2, 3, 4. Cycle 1, 2, 3. Oh, well, it's only to the foot. Uh, so this will run fine. It's an L type, so has all the stages. For the second one, uh, R0 is the fetch in the code. It's always problem free. This is dependent on this. When will it be done? After the mem stage. So then we can do that. No op and then right back. Uh, fetch this. This will be stalled here. Decode. Uh, stall here. Then fetch. Since we only need to know this, who cares? So the answer for this is write back for instruction 1, uh, exec, decode, and fetch. That should be what he gave us. Yeah, write back, exec, decode, and fetch. Yeah, okay. Okay. So for this question, actually I can probably just try it here. Alright, discussion considers the MIPS pipeline. There's operand forwarding. So, but there is branch prediction, but it's static, not taken. Uh, and you also assume when the branch on equal is executed, the value in R1 is equal to R2. So this will run the loop. So first, let's look at the dependencies. Um, over here, so instruction, the register, dependent, and so dependency on. So instruction 3, register 10, dependency on instruction 2, 2, 3, 4, 5, 6. Right. And then let's see, R14 used anywhere? Nope. How about R4? Yes. So instruction 5, register 4, has a dependency on instruction 4. This one over here. So instruction 6, R1 on instruction 5, and then 7, also R1 on instruction 6. Uh, I think that's it because there's no looping back. So these are all the data dependencies. This isn't necessarily all the data hazards. Um, okay, so what's going to happen for this? Let's think. This is always going to run. So fetch, decode, a branch, so exec, no up, no up. Since the branch predictor, it says it's always not taken, so we just fetch the next two instructions. Um, so fetch decode. After the exec, we'll know that has to be flushed. Same thing for line 3. Fetch, and then flushed. Line 4 happens to be the correct line, so it'll be fetched after the exec, so fetch there. Similar type, so fetch, decode. Does it have any dependencies? No. No. This one we can just do fetch, decode, exec, no op, yeah, no op, and then write back. Fetch, decode. We have to know the value in R4 to do this line. We can data forward it from the exec stage. So fetch, decode, exec. This is L type. Oh, I should have wrote those. L type, L type, R type, L type, R type, R type. So since this is a load, fetch decode exec, mem write back, fetch decode, and then this one, just depending on this, same thing, forward that one to this, Um, no up, right back, and then over here. So fetch, decode, and this is also another forward, I think. Is that right? There's 3 data forwards. Oh, I messed up somewhere. Oh, this is an L-type instruction. You can only data forward from the exec stage if for R-type instruction. That's right. That's my fault. So the the R-type instruction was able to fetch that, but um, for this one, we have to stall here, and then the mem after mem we can. Oh, why don't I miss everything? Oh, here, and then after mem we can exec no op right back, and we have to stall here. Decode here, and this one can because this is R type. Back no op right back. Yeah, I think no, that's right. Right. Cycle 12. Yeah. Okay. So I'm just gonna restart the whiteboard and it's recording out. Okay. So that was that, and then was there any questions on that question? Okay. So for this one, since if tag not taken, why are we starting x before exec for line 2? Yeah, so for even though it's static not taken, like he didn't mention that you have to stall until branch is figured out. So if like the PC counter still updates by 4, so you still fetch like the next instruction, the next 2 instructions actually. So it's really similar to having no branch prediction and static not taken. They're both similar, where you take just the next 2 lines underneath. So if it was branch taken, which is like the next question, then you would jump to the label immediately if it's branch prediction taken. But with branch prediction, like you either take the branch or you don't. So you either fetch the right instructions so you don't have to do anything, or you fetch 2 wrong instructions that will get flushed. So in this case, like you did take the branch, but we didn't know that until after the exec was finished calculating it. So since it was the predictor says to not take it, we 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 didn't take it and fetched lines 2 and 3, but they have to be flushed since we actually did have to take the loop, or sorry, the jump. So for this one, it's static taken branch predictor. And then this one, same thing. R1 is equal to R2. All the data dependencies, I think it's like the same thing, right? Um, so instruction, register, and then dependency on. So this is line 1, 2, 3, 4, 5, 6. Instruction 3 on register 10 has a dependency from line 2. What else is there? 14 is not used. Or 4? Okay, so it's like the same thing. So instruction 5 or 4 on line 4. And then line 6. Oh, there's one less line of code in this, I guess. R1 from instruction 5. Just, yeah, so if we just do this, this is always the same. Fetch decode, exec, no up, no up. Um, for this, we just fetch this one right away, right? Yeah, I am talking. Should be like, uh, um, let's see. So fetch decode. Is there any dependencies? No. So that this is a branch. Load R type, load R type. So fetch decode exec, no op, right back. Fetch decode. Is there any dependency? Yeah. This is an R type instruction, so we can forward the data. Mem right back, fetch decode. This is a load type instruction, so we have to stall here, and then after the mem stage, we'll know what's in R1. So then we can exec, no op, right back. So is that right? Cycle 9, finish. Yeah. Okay. Any questions? The one thing I don't understand is like, okay, there's a branch predictor, but how can we know that it's even a branch instruction until it's decoded? How does that even fucking work? Did he ever explain that? Right, but if you look, like, line 4 is fetched before, oh, you're saying it's like right after this decode? Oh, I see. Okay, interesting. Okay, so it doesn't matter. It's fine even with the branch predictor. Got it. Okay, so for this question, Um, Static taken. So we're always going to predict taken. Correct. Yes. Oh, wait, no, not for that one. For this one, this one, this one, and this one. So the accuracy is 1, 2, 3, 4, 5, 6, 7, 8. 7 out of 10 for this one. This one's static not taken. So all of these are not taken. It's only going to be correct for the opposite ones. So 3 out of 10. And then this one is dynamic 1 bit, not taken. So we start with not taken. Was it correct? No. So we flip to taken. And then this is correct. So yes. Taken, was it correct? Yes. Taken, was it correct? No. So change it to not taken. Was it correct? No. So switch it to taken. Was it correct? No. Switch it to not taken. Was it correct? No. And then switch it to taken. It's correct, yes. So keep it. Yes. And then this taken, and then it won't be accurate. So how many was that? 1, 2, 3, 4. And then for this one, it's 2-bit. Weekly taken. So start with weekly taken. Is it accurate? Yes. So change it to strongly taken. Accurate, yes. Strongly taken. Accurate. So strongly taken, but it's wrong. So we switch it to weekly taken now. Is it correct? Yes. So change it back to strongly taken. Is it correct? No. So change it to weekly taken. Is it accurate? Yes. No. So let's change it to strongly taken. Yes. Strongly taken. Yes. Strongly taken. No. So the accuracy for this is 7 out of 10. Any questions for this one? Okay. This is 1-bit dynamic not taken. Okay, so not taken. Is it accurate? No. So change it. Accurate? Yes. Keep it. So yes. Is it accurate? Yes. So keep it. Is it accurate? No. So flip it. Is it accurate? No. So flip it. It's accurate. Keep it. Keep it. No. So flip it. No. Flip it again. Yes. Yes. No. Okay. So the accuracy is 1, 2, 3, 4, 5, 6. 6 out of 12, right? Can't count. Holy shit. Yeah, 12. For this one, it's dynamic initially taken. Is it correct? Yes. So the rest of this will be the same as that. So it's just going to be 7 out of 12 because it's going to be correct initially. So one more correct. And then for this one, um, initially strongly taken. Is it correct? Yes. Strongly taken. Yes. Yes. Uh, Predict this, and then it's no. So change it to weekly taken. Is it accurate? Yes. Change it to strongly taken. Yes. Keep it. This one is strongly taken, but it's no. So change it to weakly taken, but it's accurate. So switch it back. Strongly taken. Yes. And then this will be a no. So the accuracy for this is a 9 out of 12. Um, so I guess he doesn't have the right answer sheet for the bottom part. but it's 7, 3. This should be a 4, 7, 10. Okay. Any questions on that? The branch predictor chart like this is pretty easy. Just remember for 1 bit, you always just flip it if it's wrong, and then for 2-bit, it's just uh from like you go from strong to weak, and then you flip it to the other side if you keep on getting it wrong. What else? Next question. The chart he gives in the presentation, like his notes. Yeah. Okay. So for this, there's total number of clock cycles of the above executables are executed on a non-pipeline multi-programming system, but there's no multiprocessing. So if you don't have both, then these codes have to run one after another. So there's also not pipelined, so everything has to run one after another anyway. So you just count these all up. So it's 5 plus 11 plus 8 plus 11. Yeah, there's no branches. So all these codes have no branches. Um, it's not pipelined, so one line of code has to run after another. The CPI for single cycle stuff is always the number of instructions. Um, if it was pipelined, then you have to draw out the pipeline, I believe. Um, yeah. If if there's a branch, if you skip some lines, then those aren't going to be lines that are executed, right? Um, so I mean, he might put pipeline, like, because we were all expecting last time for him to not put messy with associative mapping, and then he did. So uh, so this is 35. This is also 35. So the reason is these lines of code have to run one after another since they're not pipelined, and you have these multi-programming system but no multiprocessing, or multiprocessing and no multiprogramming. And if you don't have both, then it's basically like you have one CPU. So so these two are both 35, and then this one for the best case and worst case. So you do have multiprocessing and multiprogramming, so that's good. You can distribute the programs. The worst case is that the OS doesn't distribute these programs and all of them run on one CPU anyway. So that's still 35. And then the best case is all of these run in parallel on like whatever many processors you have. Let's say you have 4 processors to run these 4 programs. So it's just the longest one here, which is going to be 11. For this question, so it says the total number of clock cycles are executed in parallel on 4 single-cycle processors, but I'm assuming since he didn't mention like a multi-programming OS, these have to run one after another. So it's 16, right? Because it's 4 plus 4 plus 4 plus 4. And then calculate the total number of clock cycles of the above executables are executed in parallel in 4 MIPS pipeline processors. Okay, so the this code is all the same for each program, so we don't have to do it once. But let's do that then. So there's R1. Uh, me. Do I have the chart? Yeah. Okay. So for one of these lines of code, let's see, 1, 2, 3, and 4. Cycle 1, cycle 3. So the first one is an L type, R type, L type, and R type. So fetch, decode, exec, mem, right back. Are there any data dependencies? Yes, over here. So we can do fetch and decode, fine. When we try to do the exec, we need the data from R1. That data doesn't get to us until here, after this. So stall here. This will forward it here, and then exec, no op, right back. And then is there any data dependency on this? Nope. So this one fetch, we can't decode here because there's a stall. So decode, exec, mem, right back, and then stall here, fetch, decode, and then is there any dependency here? Yes, on R1 from instruction one, but instruction one is already done, so no need to worry about that. So fetch, decode, exec, no up, right back. Okay, so as you can see, there was 9 cycles total, nine clock cycles. And then since it's not a multi-programming OS, um, each of these programs will take nine clock cycles, so it's 9 times 4. So it should be 36. And then, um, so I guess that was your question, right? Oh, what if it's pipelined? You have to draw out the pipeline. Um, and then vector, which is super scalar. Uh, okay, so this is just program 2. Um, 1, 2, 3, and 4. Okay, so these fetches, since there's four of all these things, no problem. All of these can be fetched at the same time. They can all be decoded at the same time. This first one can exec, mem, and write back. No issue, because it's the first line of code. But is there any data dependency? This on this, right? So we have to wait for the mem stage. So this has to stall again, and then you can forward it here. So now it can do exec, no up, right back. Um, so these stalls, when it's a vector processor, these don't apply to below. We just have to look for the data dependencies. So this one has no data dependencies. So this can do its thing, no problem. And then this one is dependent on R1. So this also has to stall until the mem stage can give it to here. So exec, no op, right back. So it should be 7 clock cycles. Let's see if that's right. 35, 35, 11, 35, 16, 9 times 4, 36, and then 7 clock cycles. Yep. I was thinking, what happens, like, if, like, because I'm, like, thinking about, like, trick questions after, like, exam one. Like, if, like, one of these numbers is less, so then, like, some cycle might not be able to run, right? In parallel. At that point, you'll just have to know, which stages use which of these things. But I think my notes from the first exam has that. I'm not sure. I might write those later to like either tonight or tomorrow, depends on how tired I am. Okay. So problem set 17. Okay, consider the following program. Another pipeline question. Damn, there's like a lot of pipeline practice. I mean, I guess there's not that much to test on besides pipeline and branch prediction. Isn't the exam all pipeline? Is there even any other topic? It's just all related to pipeline, right? No, anything with fork, like actual code, is not on the exam. Yeah, that's unlucky. Okay. Consider the following program. 1, 2, 3, 5, 6. The 2 is not equal to 3. No branch prediction. Draw 5-stage pipeline and provide CPI. Okay. Oh, this is an L-type branch, R-type, and this is S-type. Okay. So line 1, 2, 3, 5, 6. Um, there's no branch prediction, so it will definitely fetch 4 and 5. I just don't know if it will fetch it. If it's not equal, then they will jump. Okay, they will jump. All right. So cycle 1, cycle 2. Okay, so the first line, fetch, decode, exec, and write back. No problem there. Fetch, decode, exec, mem, write back. Line 3, fetch, decode. Is there any data dependency? Yes, on R1 and R2. So we have to wait for the mem stage for it to finish on this one. And this one, the write back is done by then. So that'll be fine. So just wait for mem stage and then exec here, a no op, no op. And then these two lines, line 4 will be fetched. And then the stall, um, after the exec, does it get flushed like here or does it get flushed here? I think it's decoded here and then flushed, right? Stall. Flushed after decode. There's no branch prediction. Shouldn't it be after the exec? Because after the exec is when you find out that oh, I don't need lines 4 and 5. I have to decode on line 4. Okay, yeah. So this is right then, hardworded. Yeah, it's exec on line 3, but he's saying that it's flushed after this decode on line 4. Okay. So then line 6 is the actual line that needs to be fetched. So fetch, decode, is there any dependency? Yes, over here, but line 4 is flush, so that won't happen. And also here, the line 1 is long done. So no data dependency there. So fetch, decode, exec, mem, and then no op. CPI for this is 11 cycles over 6 instructions, right? Let's see, that right? Total instruction. Oh, completely executed? Bruh. So when we do the cycles over instructions, it's only instructions that actually completed. Yeah, I didn't realize that 4 and 5 don't count because they didn't fully finish. That makes sense. Did I write the thing right? Let's go back, line 3, line 4 is fetched at cycle 6, flushed out there. No, line 4. Did he typo? Shouldn't this be for line 5 and then he forgot line 4, right? I'm not going crazy, right? For like just the I understand why it's 11 over 4. I'm just talking about like I have 4 and 5 both were fetched, but he only has line 4 fetched. Yeah, I'm pretty sure 4 and 5 both would have gotten fetched. And then this literally looks like his instruction 4, so I think he just forgot like the previous line. Yeah, I mean he doesn't fix his things. Like, I don't know. Kind of annoying. Okay, so this one is for static taken. The same as before, where 2, 3, 4, 5, 6. Okay, so I'm gonna copy the code. Okay, so fetch decode exec mem right back. Fetch decode. Is there any data dependency? No. So exec mem right back. So fetch decode. Is there any data dependency? Yes, same as before. So stall here. Um, we can get it here, and no up, no up. And then since there's a branch prediction and we always take it, right after the decode, we'll fetch here this instruction, right? Um, we'll have to stall here because the stall goes up to here. Um, decode. Any data dependency? Yeah. Uh, line 1 will have finished by then though. Okay. So eventually stall decode exec mem no op. So this is 9 divided by 4 instructions. Is that right? Yeah, okay. Okay. Any questions on that? Yeah, because this one, the second question was asking, it's the same as before where 2 doesn't equal 3. But the branch prediction is set to static taken. So since we have a branch predictor that always takes the branch, we had to go from line 3 to the label, which is on line 6. If they were equal. Um, so what would happen is the branch predictor, yeah. So we take this, right? And then we stall here, we decode here, and then, oh, we actually didn't need to take the branch. So flush it here. And then um, we actually have to fetch the correct instruction here, which is the next line after line 3. So then we do fetch decode. Does line 4 have any data dependencies? Yes, on line 1, but there's no, it's already finished by then, so fetch decode, exec, no op, right back, and then line 6, fetch decode, line 5, dependency, yeah, over here, but we can data forward, no op, right back. I think that's what it would be looking like. What do you think? Um, I mean, I'm kind of lazy. I didn't move 6 up. It should be like 1, 2, 3, 6, and then 4, 5. So it should be like, oops, why is this not working? Yeah, you get what I mean. Yeah, 6 would be above 4 and 5. I was just lazy. Okay, okay. Mixed pipeline. Uh, crap. Memory addresses equal 2. Registers equal 1. Any branch prediction? No. Okay. This question I haven't done, so if I make a mistake, let me know. Let's see. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And then uh R type, R type. Oh yeah, don't forget that these are R types even though there's no plus because there's no brackets around these. So these aren't L types. Um L type, R type, L type, R type, R type, and then branch. Okay, so 1, 2, 3, 4, 5, 8. I'm assuming there's gonna be some loop, right? Yeah, this is the annoying question, right? And this is the one he did in class or something, right? Okay, so first line, fetch, decode, exec, no op, write back. Same thing here. Fetch, decode, exec, no op, write back. Line 3, no problem there. No data dependency. Fetch, decode, exec, mem, write back. Line 4, yes, there's a data dependency. Yep. Line 4 has dependency on 2 and 3. So yeah, one over here and then another over here. So this will fetch and decode, and then we have to look for the data dependencies, like we said. So line 2 is an R type, so no problem there. Um, what about line 3? Line 3, we have to wait for the mem stage to finish. So stall, forward it here, and then exec, um, no op, right back. Line 5, data dependency, nope. So fetch, stall, decode, exec, mem, right back. R6 over here. R4 from line 4. Oh, oops. So stall here, fetch, decode, and then 6 is dependent on 4. Is 4 done? 4 is done. Or, well, we can forward it from exec, and then what about 5? It's an L type, so same situation. So stall here, forward it here, exec, no, I'll right back, fetch, stall, decode. Okay, line 7. Any dependency? I don't see an R3 up all the way up here, but done by then. So exec, no up, right back. Line 8. It's a branch, so stall here, fetch, decode. And then there's no branch prediction for this question, right? Okay. And is there any data dependency? Yes, from line 7, but so we can data forward it here. Exec. Um, you know, since branch is the last line, it won't fetch anything, right? It has to wait till exec for branching for fetching the next. Uh, I forgot what he said in class. Does anyone know? Basically, there's no branch prediction. So what they're asking is like, since there's no like line intent to fetch, do we just have to wait until the exec stage to like fetch line 3? Dara said that that's what he said. So we have to wait until the exec. You're saying fetch here? So yeah, just like the line number is wrong though. Yeah, okay, makes sense. So it should be line 3 and then fetch decode. Line 3 is what? And I'll type. Is there any data dependency? R1. Is there any R1 here? No. Oh, you probably should have checked what R3 you would have. Uh, R3 has 100. Okay. So this is what, like 100 loops of this crap? Because it's initialized with 100, and then every time R3 is subtracted by 1. So that's 100 loops, right? Between lines 3 and 8. With no predictor, it takes and flushes if wrong. Yeah, this is only like a weird situation because it's the last line of code. Yeah, that's what he said in class apparently, and then also on his answer key it's written like this too. So, okay, so this CPI shit is like really confusing. Um, so lines 3 through 8, right, will run 100 times. Why don't we stop pipelining after writing fetch for line 4? Uh, no, because there's a loop, no? This is this part will happen 100 times. Like I'm writing it more, but like you can write like one 100 times like this thing. I mean, wouldn't we cut off the pipeline at the overlap when calculating CPI? Yeah, so I think so what did he say? So there's these two lines are independent of that. So there's six cycles here, right? And then that's two instructions. And then what is there? Plus for the instructions, there's 1, 2, 3, 4, 5, 6 lines of code, right? 1, 2, 3, 4, 5, 6 6 lines of code that repeat itself. So 100 times 6 plus there's nothing else, right? After, since there's no branch prediction, after the final line is fetched. So I think it's just 2 plus 100 times 6, right? This is the bottom part of the equation, which is just the instructions. Um, over here, it's let's see, 1, 2, 3, 4, 5, 6. Oh, 14. Yeah. So what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 100 times 12 cycles, right? And then the last time there's going to be how many cycles? 15, 16, 17, 18, 19. I don't know. Is that right? Did I? No, did I do that right? Plus 2? That came after E. Is it 10? Did I fuck up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, it's just up to this, you're saying? Why is it up to here and not up to here? That's why I was confused when he did it in class. Cycle 13 and 14 overlaps. Oh, I see. So like from here, you're saying? Because like, okay, there's 2 cycles here, but it overlaps with like these over here. Oh, I see. Oh, that's gonna be so annoying. I'm definitely gonna fuck that up on the test. And then where's the last 2 cycles coming from? Because there's no overlap at the end over here. So what's the final answer? 8 plus 1,000 over. Did he write it out fully or what? 1,000 over 602. How did we get the 10? Okay, so you see how lines 3 through 8 are looping, right? That part you get? Yeah. And then you have to see which cycles are considered in that. So that's 1 cycle here, 2, 3, up to um, right here. And we don't consider these because the next loop has these cycles overlap with these cycles. So it's only actually up to here, um, like this this part over here that keeps on looping. Because like, or actually, did I draw that box right? Okay, up to here, right? No, up to here. Because these and these will overlap from, this is like the, after the loop restarts. So we only count those cycles that aren't overlapping with the next iteration of the loop. So that's from here to here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for the equation, uh, if we just go by the fraction, let's do the bottom part first, because that's easier. There's these 2 instructions don't loop at all. So that's 2 instructions. Plus, there's these 1, 2, 3, 4, 5, 6. Oh, sorry, 6. These 6 lines of code that will loop. So that's 6 times 100. And then on the top, there's these 2 lines, which is up to 6 cycles here. So 6 plus 100, and then times, it's like the thing that I said, where it's the stuff that doesn't overlap, which is 10. And then at the last bit, you have to count the part where it was overlapping for the last time, which would be this right here, because we weren't counting this last time, just 2 more cycles. answer should be what? 8 plus times 10. Well, just over 602. What did he write? 2 times, yeah, 2 plus 10 times 100 plus 2. Wait, shouldn't it be 6? Why did he write? That's a typo, right? Like, there should be 6 cycles, right? Oh no, there's a overlap with that too, right? Oh shit. Right, right. Because it's since the loop starts from here, the only cycles that are exclusive are these two, right? Oh my God, I'm gonna fucking mess this question up, dude. Basically, you isolate. Okay, so I think what we can do is isolate the loop part. So we know that this part will loop. Um, and then we only go up to the part that keeps on looping. And so like since this part is the second loop, we don't want to consider that. So box out like this. And then that's 6 lines of code. And how many cycles is that? It's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And then we have to consider these cycles over here. And we have to consider these cycles here at the end. So that's 2. 1, 2, and 1 and 2. So I think I'm literally gonna box out any type of loop and then just count the columns from here. So 1 column, 2 columns, and then 1 column, 2 columns, and then the loop part over here. I'm gonna do 10 times whatever the amount is. So I think now that I think about it, it's not that bad, but I feel like I'm gonna make a mistake anyway. We're going through like a lot of problems at once, but yeah, it's gonna be annoying as shit. Uh, can't we technically start fetch of line 3 in cycle 12 when branch? So there's no branch prediction, and also it's the last line of code, right? So there's no line in 9 and 10 to fetch. So we have to wait for this branch to actually calculate um where to go. You're not, well, it's not really like a stall per se. It's just that like normally there was no lines of code left to run. Does the CPI become more annoying if there was like a line 9 and 10, by the way, or is it like the same idea still? It becomes more annoying? Oh God. Is there an example question like that, or no, we don't have one? Which question is on the exam? Okay, well, I'm gonna skip this one. I'm tired of doing these. I'm looking for one that's like more annoying, I guess. Uh, we've done these already. This one's easy, I think, right? Should we do problem set 19? Okay, so I'm gonna skip, oh, whoops, problem set 17 and, sorry, yeah, I'm gonna skip problem set 18 and the second part of problem set 17 unless like anyone wants to do it in particular. I think it's like more of the same shit. I'd rather do the exam one with like the 2 extra lines. Okay, so I'll do problem set 19 and I'm gonna take a break. I mean, how long does everyone else want to study for? A lot of the exam questions are problem set questions. Okay, we'll see as we go. Um, okay, so I'm gonna do problem set 19 and then take like a 15-minute break probably, if that sounds good. And then we can start doing the exam questions. Um, Let me do problem set 19 and then we can take a break. Let's see. Branch predictor, dynamic, taken, spell, taken. Okay, there's no branch, so we don't have to write anything, right? So it's just this line of code, this line of code, and this line of code, or what? Okay, so the predictor value is going to start with the taken. We have to calculate what these are. So 1 and 2 is not equal, so it was wrong. Um, what does it mean by predictor accuracy? Do we write yes or no, or like what do we write? Do we write like what if reality was? Do we write like this or no? I don't know. Accuracy is just at the end. Okay. Um, so now it'll change to not taken, right? Well, yeah, because we jumped from here to here, right? Branch on equal, no, we don't jump. So we just run these lines of code. That's fine. But the next time we see a branch, it'll be not taken. And then R5 minus R5, 0. So it'll be equal. So we did take the branch. So it's also wrong. So the next time we see a branch, it's going to be taken. And since this time we did, we moved to here. Uh, R4 gets a 4. Um, so that's 4 is equal to 4. So yes. And then this jumps to this. So that's it. Okay. So, and then what? Do we just write like an actual thing or no? Like 1 out of 3 accuracy or something like that? Or, uh, yeah, I can do it again. Okay. So for this question, uh, there's lines of code, but the only ones we care about are branches. So one here, and one here. If there's also like a BNE, that also counts as a branch, right? So, uh, so we start with dynamic 1-bit initialize to taken. So the first time we're going to predict that we're going to take it. And then we check. So R1 has a 1, and then R2 has a 2. So this one said if it's equal, then take the branch. And they weren't, so we don't. So it was a wrong prediction, right? Because 1 is not equal to 2. Um, so then this line of code will run. Here we have to know what's in R5, but anything minus itself is going to be 0. So 0 is equal to 0. Oh, by the way, since this was taken and then it was wrong, the next time it'll flip because it's a dynamic predictor. And then in reality, what's going to happen? Oh, did I mess up? Oh, yeah, I did. Uh, this was a yes, actually. I think that's why you said 2 out of 3, right? You probably did the problem set yourself and you got 2 out of 3. Because 0 minus 0. Yeah, sorry, yeah. Whatever, it's going to be 0. It's equal to 0. Oh, no. Wait, we do take it, right? I'm confusing myself. I think I should write the actual what we take. Yeah, okay. I think in reality, we should say what we do. So this one was branch on equal, and it wasn't equal, so it was not taken in reality. Um, this one was branch on equal, and it was equal, so it was taken in reality. So now if we compare these, they're wrong, and this is wrong. Okay, I think we should do it like this. Okay, so this one, we actually did take the branch, so that means we jump to this line of code. So this line of code will run, this line of code will run, and this line of code will run. And we see here, okay, well, what's in R4? 4. So 4 is equal to 4. This is a branch on equal. So in reality, we will take this. And since we were wrong here, their next prediction was going to be taken. And this time, these are equal, so it's a yes. So the accuracy was 1 out of 3. Okay, so for this question, let's see. We have one here, another here, another here. Is this the same code, I guess? Okay, so this one is 2-bit with a strongly taken initialized. I can't spell. So our predictor value is strongly taken. They're the same as before. 1 is not equal to 2. This is branch on equal, so this is not taken. So this was wrong. So the next time it'll change to weakly taken. And this is the same as before. Whatever, anything minus itself is 0, so 0 is equal to 0. We do take the branch, because it's branch on equal. And this, weakly taken is a taken, so that's accurate, yes. And the next time we do a branch, it'll change to strongly taken, because we were accurate. Same thing here, R4 and 4. We had a 4, so 4 is equal to 4. Branch on equal, so we take it. And predictor accuracy is yes. And then X goes to here, that line of code. So this one is 2. Okay, any questions? Okay, so do a 15-20 minute break. I guess around 10 o'clock. Everyone come back. I'm gonna be chilling here. Just don't feel like there's problems right now. Okay, pause the recording.